Hello everybody, welcome. Welcome to 225X. This is an edX version of a class that I've taught at MIT for a number of years called 225, which is an advanced class in fluid mechanics. So first question you might be asking is, what is fluid mechanics? Why am I here? What am I interested in? So fluid mechanics is a branch of continuum mechanics. So, which it's a branch of what we'll call continuum mechanics that describes the motion of fluids such as air or water. So those may be ones that you're very familiar with, but also you might be interested in the flow of other things, for example, blood, or maybe even yogurt, or something even much more viscous, say lava. So many materials are fluid in nature, and we're interested in trying to describe their flow. And I've used this term continuum mechanics already, and so we should define what we mean by continuum mechanics. And a continuum is the idea of a contraction of two words, which is what we'll call a continuous medium. So if we combine those words, we get the idea of a continuum. And the key idea behind that is that we're going to treat these materials in such a way that we can think about a little piece of material, which we might call a material element, and we'll neglect the molecular nature of that material, and we'll just treat it as a single piece of matter, and we can describe, for example, its velocity as a function of position and time. And so when I write an underbar, we're going to mean a vector, which is a function of a vectorial position, so relative to some origin, and how it evolves in time. And so we're going to be interested in all these different kinds of materials and how they flow. This gives rise to a related question that you might be asking, though, is what does it mean to be a fluid? So related question, what is a fluid? Well, the ancient Greeks would have defined this in a certain way. They thought that there were four states of matter. They thought that there was earth, wind, fire, and water. And three of those states we might think of as being fluid states. That is, the definition of a fluid is that it's a material that flows under the action of a shear stress no matter how small it is. So what does that mean to flow? Well, let's think about taking a small piece of matter. Let's take a blob of material and place it on a solid surface. And then think about deforming it under this idea of a shear stress. So a shear stress we can represent as a sliding force acting on this. So that'll be a force divided by the area over which I'm contacting it. So the force divided by area has units of a stress in SI units. That would be in units of newtons per square meter, and I'll use square brackets here to indicate this. And typically we'll represent the shear stress by a variable in Greek, a Greek variable tau, and so tau here is a shear stress. Now, as we move on, we'll recognize that in fact the stress is a tensor, and so we're going to need indices on this to indicate which component of a tensor we're thinking about. But for now, we're just going to think about it as a scalar, and we're going to think about what happens. And so if we deal with a solid material this way, if I deform a solid material this way, then the material will deform a certain amount after some time, and then it will stop and it'll achieve a new equilibrium state that will no longer flow. And so this would be the shape of the material at time t1. A good example, which will tell us in the future about what the time of year it is that I'm recording it. If I take my mask and I think about deforming a material, it'll deform a certain amount under a stress, and then it'll stop deforming. And of course, if I let it go, then typically I'll get that energy back and I'll get elastic recoil. And so this energy is recoverable. This would be what you would see in, for example, a solid state of matter. However, if we deal with a liquid, then in fact actually what we'll find is that the material doesn't stop deforming. And at one instant in time we'll find that it maybe has taken a shape like this. At another instant in time it will have taken another shape, and it'll continue flowing under the action of a shear stress. So this would be the shape at T1, T2, T3. And a fluid will just continue to flow under the action of that shear stress at all future times. And so we're going to be interested in this class in thinking about materials that deform like that. The real world is a little bit more complicated than this. So here's a material that we might think about deforming. So this is a material that maybe we'll think looks like a solid. It doesn't deform very much at all. It looks like it's staying there. But eventually, if I pull on it fast enough, then indeed I can get this material to flow and it'll come out of the container. And so it's not at all clear whether this is really a fluid or a solid. And in fact, we really need a finite shear stress before this material will flow. If you brushed your teeth before you came to this lecture, you've also encountered another material like that, which is toothpaste, which also requires a finite stress before it will flow. And so the real world's a little more complicated than this. So this caveat of no matter how small leads to the idea of what we'll call Newtonian fluids. So a Newtonian fluid is one that will flow under the action of something that no matter how small. Some materials, however, need a finite shear stress, so if they need a finite shear stress to flow, then that's a good example. For example, we've talked about toothpaste or silly putty. Or frequently, even some materials in this list that I mentioned here, like yogurt, will sit on a spoon quite happily. So you'll pile yogurt up on your spoon, and it won't flow under the action of gravity. It'll sit there quite comfortably. But eventually, with a large enough stress that you might put when you put it in your mouth, then it will flow. And these are examples of materials that people would call non-Newtonian fluids. We won't be thinking about those in this class. So 225 is really only going to focus on this class of Newtonian fluids, i.e. things that will flow under an action of a stress no matter how small. A corollary of this that is useful to think about So a corollary of this is the idea that a fluid at rest exists in a state of hydrostatic equilibrium, where there are no shear stresses. Acting on it.